Okay, so let's see some problems based on the Butterworth filter. Okay, so here I have done two problems. Okay, and both of them are based on low pass filter. Okay, so how are you identifying that it is a low pass filter? Uh, you should I'll tell you here. Okay, let's look into the first problem and we'll see. Okay, now here it is given for the given specification design an analog Butterworth filter, and these are the specification given. Okay, all right. Now in order to find the transfer function, we know that we need to calculate the order and we need to calculate the cutoff frequency. So in the previous video I have explained about the steps. Okay, there were around 5 steps, okay, of how actually you need to design an analog Butterworth filter. Okay, so you just go through it. Okay, to know what and all you will have to find. So first thing what you will have to do, you will have to find the order with respect to the given specification. Okay, so you can write down what and all things are given in the problem. Okay, then find the order. From that order is nothing but n. So usually what we calculate and get will not be an integer value of n, so we round it to the next higher integer. Okay, then we find a transfer function, that is h of s, for the cutoff frequency, that is omega c equal to 1 radian per second. Okay, then we would calculate the cutoff frequency and then we will find the corresponding transfer function with respect to the value of the cutoff frequency omega c that you have found out by substituting s is equal to s by omega c. Okay, so these are the 5 steps that you need to follow for designing a analog Butterworth filter. I repeat the steps. Given the specifications of a particular problem, you need to find the order. Order is nothing but capital N. You have to find out the value that you find out of the formula will not be a integer. Okay, so you will have the fractional part of it. So what do? Is we round it to round it off to the next higher integer value. Then we would find the transfer function h of s considering our cutoff frequency as 1 radian per second. Okay, then we would find the actual cutoff frequency, that is nothing but your omega c. Okay, then considering your cutoff frequency of what you have found out, okay, we would alter the transfer function that we have derived by substituting s equals to s by omega c. Okay, these are the steps that you need to follow. Okay, so I've written those steps you have in the notes, okay, and given in the previous video. So kindly go through it if you have confusion in what I said just now. Okay, alright. So now since this is the first problem that we are doing on the Butterworth filter, you might have confusion how to take out the specification. What are these values given? Okay, now if you compare this particular specification given with whatever frequency magnitude response we had, okay, you again go back to the video, okay, the first video of this chapter, introduction. Okay, therein we had a graph and we had written this. Okay, that is for the frequency lying between 0 to your, what is this, omega p, that is nothing but the h frequency of your pass band, that is nothing but this. So starting from 0 to this, okay, you have your, what is this, magnitude of the frequency response, okay, given by 1 minus del p to 1. So this is, this particular value h of j omega is lying between 1 minus del p to, you consider you have your 1 somewhere here. Okay, you have your 1 somewhere here. This is the 0 dB I have represented. Assume you have 1. So this is lying in between those. Okay, for what frequency? From 0 to omega p. That means, see, this is forming your pass band starting from 0. If you consider this axis to be a frequency axis represented by omega, from 0 to omega p you have the signal passing through. After that you have your transition band and your stop band. So I understand that this is a low pass filter that is allowing low frequency signal. If I would have had a high frequency filter here, it wouldn't have allowed the signal to pass through in in the initial duration. Okay, that is, we will not have our pass band in the initial stage. You will have your stop band here, then you will have your transition band, then you will have your pass band. That we'll see in the later stage. Okay, pass band, band pass and all that designing, not now. Clear? Okay. Now, so if you compare these two, you can see 1 minus LP is nothing but your 0.9. Correct? Okay. And what about your del of S? That is nothing but your 0.2. So I have written 1 minus del P 0.9, del S is nothing but 0.2. What is your omega P? What is your omega P? That is nothing but 0.2 pi. It is radian. Okay, it is in radian per second. And what is your del S? It is nothing but your 0.4. Clear? Okay, alright. Now, see, we want the value to be in dB. Now, you know that if 1 minus del P and del S is given, you refer back to the graph in the first video again. Okay, there, this was 1 minus del P and this was your del S. Now, if you have to, so I have written the value as it is here, 0.9 and 0.2. You need to convert this into your corresponding dB value. And always remember that the dB value that you obtain, okay, the value of your attenuation AS and AP, you will have to have in dB, and that will be always negative. It has to be negative. Okay, why? Because AS and AP is representing nothing but attenuation. That means it is loss. So that minus sign, it is indicating that it is somewhere less than the ideal value 0 dB or 1 dB. 0 dB you consider. Okay, so it will be lesser than that, indicated by this minus sign. Clear? Okay, so dB scale it is. So AS and AP is attenuation, it is loss, it will not be positive, it will always be in negative. Clear? Okay. So 1 minus del P is given, del S is given, omega P and omega S is given. So you have to convert. So we have the formula for finding the order N, that is given as this. Okay, we have derived it. Okay, so you go through the derivation, the end equation was this. Further we had simplified it. Okay, further simplified, it was for the ease of notation. Okay, when you expand those what do you say, the formulas, then formulas that we had obtained after the derivation, that was nothing but this. Any one of that you can follow, but output will be the same thing. Okay, so I have picked up this, so it is nothing but N equal to, check in the derivation whether you have this. Okay, you will have this, log of root of, this is a root over both. Okay, 10 to the power minus 0.1 AS minus 1 by 10 to the power minus 0.1 AP minus 1, root of this. Okay, so AS is nothing but 20 log. If del S is given, if AS is given as it is, it's completely fine. If not, you have to convert that. Okay, this is not given in dB, so AS is 20 log del S, so you get minus 13.997. Similarly, AP 20 log 1 minus del P, so you get this value. Substitute the value of AP and AS in this, and omega S and omega P already you have. Okay, so 10 to the power, so you have your minus here. Okay, minus that becomes plus here. Substitute the value, you solve it further. So I have written 10 to the power, okay, I have log of this thing by 2 log. No, what I have done, I have not taken root, I have assumed this as into, instead of root, 1 by 2, so that 2 I have taken down, so 2 log. If you solve it like this also, you will get the correct answer, same answer. Okay, so you are getting the solved value of N is 3.337. So the second step is nothing but you are rounding it off to the next higher integer. So you have rounded it off to the value 4. Okay, alright. So now N is 4, so we are trying to find the poles. Okay, in order to find the transfer function H of S, you remember, if it is 4, then you will have 1 by S minus S0, S minus S1, S minus S2, S minus S3. Okay, so if it is N is 4, so that means the K value would range from 0 to N minus 1, that is nothing but 0 to 3. So that means you understand that you will have basically 4 poles lying on the left hand part of the what do you say, the circle that you have. Okay, so axis being your J omega. Okay, the poles calculation. Okay, So sk is e to the power j phi k. This also we have done in derivation. That's why I told you derivation is important. You need to go through and understand it to understand the problem, or else it will be difficult for you. Okay, so this, what is this phi k? We found out phi k was pi by 2 plus 2k plus 1 by 2n pi. Okay, so first is n is equal to 4, so your k will be from 0 to, I have not written here, you please mention, k is from 0 to 3. So first value in this particular formula, that is see, k instead of k I will be substituting 0. So pi by 2 plus this becomes 0. You will get pi by 2 plus pi by 8. N is 4. Okay, n is 4. So you will get 5 pi by 8. Now if you have 5 pi by 8, what would you do? How are you getting? So your S naught is equal to e to the power j 5 pi by 8. That is nothing but you will have your cos 5 pi by 8 plus j sine 5 pi by 8. Okay, so you will have this value. Similarly, you will calculate for your phi 1 what angle you are getting. Okay, then your theta value, then S1. Similarly, phi 2 S2, phi 3 S3. So how will the transfer function look like for n equal to 4? 1 by S minus S naught, S minus S1, S2, S3. Okay, alright. So whatever you have obtained for S0, S1, S2, S3, you will be substituting here and solving it. Now one thing I want to tell you, if you find it difficult solving this is much easier. Okay, if not, if you remember, we had a table in the last video, you can see, wherein we had calculated the different polynomials for your different value of your order. So we had calculated from, if I am not wrong, from 1 to 5, right? If I am not wrong, we had calculated from 1 to 5. Okay, you just go through it. So if you, yes, we had calculated from 1 to 5. So direct Butterworth polynomials we had calculated. We had derived for 2 values and we had rest of the values with. So if you remember that, and if you can after this particular step, substituting the value that you have calculated, after that if you can directly, if you remember that and if you can directly write it, it's fine. That is also considered. Or else if you can solve it, that is also fine. Clear? Okay. So omega c, now the cutoff frequency is given by omega p by 10 to the power minus 0.1 AP minus 1, it is not very clear here, minus 1 into 1 by 2n. So your n is nothing but, so omega p, you know what is omega p, and this is calculated. AP you have calculated 1 by 2 n. N is nothing but your 4, right? And you have calculated 4. So I have already taken the square of it. Don't think like n is only there. What happened to this 1 by 2? I have already solved it for 10 to the power minus 0.1 AP minus 1 whole to the power 1 by 2. This is that particular value, and then 1 by n, that is 4. However you calculate, it should be this. Okay, so your cutoff frequency is this. Now how is the transfer function changing? Transfer function for the cutoff frequency of 0.24 pi will be given as by replacing s equals to s by your omega c. What is omega c? 0.24. So you are replacing your s by wherever you had s in the equation on the transfer function that you have calculated, you would be substituting this by 0.24. So if it is easier for you to solve it without taking much time, fine, or else this is also acceptable. Clear? Okay, fine. One more example. Let's see one more problem. Okay, now here they have given past tense. This particular problem I have given in Ganesh, taken from Ganesh. See, in Ganesh, the way the problem they have solved is different. The formula for n also they have derived it differently. I would suggest you just see the question there, but solve in the way that we have done here with the proper derivation we have done. How exactly we have got the terms here, we have clearly mentioned. So do not get confused. Okay, he used some other method, so we have understood it and taken it from your his book only, prescribed book. So don't get confused. Problem question you take from there, solution you solve it by this particular methods, like what value for n we have taken, how we have calculated there. Instead of AS and AP, they have used KP and KS, which is not needed. Okay, so we have proper derivation, so I would suggest you use this particular method. Okay, alright. So whichever you stick on to one particular method, it's not that one problem you're solving by one and another is solving by another method, and you will end up confusing yourself, because this chapter consists of many more topics. Okay, alright. So now here they have given passband gain as Kp. Okay, so Kp 1 dB. Ignore this, they had given minus, it will not come minus here. Okay, Kp you consider as 1 dB at omega p. Stop band attenuation they have given, that is your omega s. Omega s is 8 radian. This is nothing but your stop band attenuation as. Okay, 20 dB. So omega s you have, omega p you have, Kp they have given, Kp equal to Kp and Ap you have to relate. This is the gain. Gain will be positive. In Ganesha they had given minus. It should be plus. Okay. So 1 dB. Okay. 1 dB. So Ap is equal to minus Kp. For calculating the order n, capital N, we want AP, right? So AP will be equal to minus Kp. So 1 dB you can consider minus 1 dB, and I already told you that it is since it is loss, since it is attenuation, okay, that we are making use in calculating our n, it will be in minus value only. So AP will be minus 1 dB. So they have given A is 20 dB, that is nothing but minus 20 dB. Omega P and omega S they have given. So here also you can understand, see, omega P passband is 4 radian per second. After that you have your omega S 8 radian per second. So we consider this to be again a low pass filter result. Okay, usually they have the tendency to mention it in the problem, whether you are designing low pass, high pass, band stop, or whatever it is. Okay, alright. So same way, however you have solved it, you can solve it. So n equals to log of the same formula you use, substitute the value, you would end up getting 4.29. That means n is 5. Okay, so you will have k ranging from 0 to 4, 0, 1, 2, 3, 4. So similarly you will find S0, S1, S2, S3 and S4. Okay, by finding your 5.1, 5.2, 5.3 and 5.4. Okay, starting from 5.0 to 5.4. Okay, so 5.0, S0, 5.1, S1, 5.2, S2, 5.3, S3, 5.4, S4. Okay, then what you have to do? So h of s, the transfer function will be equal to 1 by s minus how many poles that you will have, you have calculated. So s minus s0, s minus s1, s minus s2, s minus s3, s minus s4. Substitute all the value, solve it if you can. Otherwise, if you know for n equal to 5, what is the polynomial that we had found out, okay, you can directly write it. Then you find the cutoff frequency, that is omega p by this. Okay, calculate it. So for the transfer function at, okay, at omega c equal to this particular value will be nothing but you substitute in the above equation. Instead of s, you will be substituting by s by omega c, whatever value you substitute in the above equation, and you solve it or leave it till here. If you can solve it, fine, well and good. Otherwise, consider here. So this is how it looks like. So omega p is 4 radian per second, omega is 8 radian per second. So this is your AS, this is your AP. Again, see, it is minus here. Okay, it has to be, AS and AP has to be in minus only. Okay, since it is an attenuation that you have here. Okay, hope it is understood. If you have any confusion, you can ask.